Next, after type 1 from the model 1, so in this model 1, now we'll solve the type 2 problems, which are called as tensile test problems. So we'll take an example and we'll solve this. So example 1. So this is solved. So following data refers to a master specimen. So the data first is diameter of specimen, D is 25 mm, gauge length of specimen, capital L is 200 mm, load at yield point 150 kilonewtons, extension of specimen under the load of 20 kilonewton is 0.04 mm, maximum load to 25 kilonewton, length of specimen after failure to 75 mm, neck diameter is 18.25 mm. So this is the given data for the problem. As you know, the D is 25 mm diameter. Gauge length is nothing but the original length of the specimen, 200 mm. Load at yield point. So after conduction of test, they found that the load at yield point is 150 kilonewton. And after conduction of the experiment, after breaking, they found that extension of the specimen under the load 20 kN after was 0.04 mm. Maximum load attained was 225 kilonewton. Length of specimen after failure means after cutting of specimen, joining them and just measuring the final length, they got it as 275. This is the final length. Neck diameter is nothing but the final diameter. Means it formed necking after breaking. So that necking is called neck diameter or final diameter, 18.25 mm. So they have to determine Young's modulus E, yield stress sigma yield, ultimate stress sigma ultimate, fourth one percentage elongation, fifth one percentage reduction area, and sixth one safe stress opening phase of 2.5. So taking one by one. First we'll solve for Young's modulus. Now to find Young's modulus E, always take a load lesser than the yield point. You should always take the load below the yield point, and where the elongation also is given. So in this case, 20 kilonewton is less than the yield point, that is 150 kilonewton. It is less than yield point 150 kilonewton. Also the elongation is given, that is 0.04. And so by using the formula, delta L equals to FL by AE. So delta L is 0.04, F is 20,000, and F is 20,000. L is the original length, that 200. A is area of cross section, that is pi by 4 d square. This d square should be the original d, that is 25 mm square, into E is unknown. So simplifying the equation, we can get the answer for Young's modulus. Next, second comes yield stress sigma yield. Yield stress sigma yield can be just used by the formula yield load upon original cross section. So yield load here is 150 kilonewton or 115 10 to 3 newton upon original area pi by 4, 25 square, original diameter square, 25 square. We can get the yield stress. Ultimate stress, again sigma ultimate is nothing but ultimate load, that is maximum load upon original cross section area. Ultimate load here is which is nothing but maximum load, also called as ultimate maximum, one of the same, that is 225 kilonewtons, 225 10 to 3 newtons upon original area pi by 4, 25 square. So next, percentage elongation. Next we should find the percentage elongation. So percentage elongation formula we know already. So LF minus LO upon LO into 100. LF is the final length, that is after breaking, that is here it is given as 275. Original length, that is gauge length, that is 200 upon 200 into 100. We get the percentage elongation. Next, percentage reduction area. So we also know this formula, original area minus final area into original into 100. So original area we calculate by the formula pi by 4, 25 square, diameter specimen, original diameter specimen 25 square, and final area will be pi by 4 18.25 the whole square. So you get the final area AF. Substituting the values in this, you can get the percentage reduction in area. Now safe stress or working stress. So safe stress is nothing but, since it's a mild steel, it's a ductile material, so you have to take the yield load here, not the ultimate load. So you have the safe stress. So the working stress, the formula is yield load upon FOS. FOS is equals to yield load upon working stress. So therefore yield stress you have to take one yield stress you have to take upon F divided by FOS, that is 2.5. So we'll get the working stress. So we'll take an example here. Following data refers to a master specimen in a laboratory. The diameter specimen 25 km, gauge length of specimen 200 mm. The same problem here. So for Young's modulus, so to find Young's modulus, first we have to find a stress load by area, that is 20,000 upon pi by 4 d square. So 20,000 by because we should take a load less than the yield point. So yield point is 150 kilonewton and 20 kilonewton is less than 150, so we can take 20 kilonewton, and the stress is 40.744. Strain is delta L by L. Delta L here is 0.04 upon L is 200. Substituting the values of stress by strain, you can get the Young's modulus also. Now yield stress. So yield stress is load at yield point upon original cross-section area. Load at yield point is 150 10⁻³ newtons. Original cross-section area is pi by 4 25 square, so we get 305.58 newton per mm square. Next, ultimate stress. We know that ultimate stress is a maximum load or ultimate load upon original area. So maximum load, as we know, it is 225 10⁻³ upon pi by 4 25 square, so therefore 58.336 newton per mm square. Percentage elongation is total increase in length, so the total increase in LF minus LO upon LF. LF is 275, as you can see LF is 275, LO is 200 upon LO into 200 into 37.5 percentage of increase or elongation. Percentage reduction area, original area minus final hour upon original. So original pi by 4 25 square minus final pi by 18.25 square whole upon original, that is 85 by 4 25 square into 100, get 46.7% of reduction in area. Lastly, safe stress is yield stress upon factor of safety. Yield stress was 3.58 upon factor of safety is 2.5, so you get 1.22 newton per mm square.